Hi everyone. I figured it would be good for us to take a look at one of the examples that the book has that dealt with dealt with sample distributions and using a sample distribution to find an average. So we're going to be taking a look at 11.8, which is on page 305 in the text. Before we do that, at the very top of the page, it has four charts. And let's just say that these charts are basically the distributions for how long it takes to service an AC unit. All right, so there's thousands of these units out here, and this first part, this is the top left corner, A, shows us the distribution of these, and it says that it has a mean of 1 hour with a standard deviation of 1 hour. All right, so really there are some units, a lot of units, that take no time to service, all right, probably because they're not broken. But some units are going to take quite a bit of time. Now, I don't know how many units of this air conditioner there are. There's probably thousands, if not hundreds of thousands of these air conditioning units in apartment buildings and people's houses all over the place. So what 11.8 or what these four charts show is that as you start taking random samples of these, so let's say we sample 20, I think the first part, B, C, and D, if we take a sample of two of these units and measure it, like we're basically taking a random sample of 2 units. All right, this is basically what the distribution looks like. All right, sometimes we get 2 units that don't need any work. A lot of times, though, we get 2 units that look like they need about a half hour of work. And every once in a while we get, and this is an average, the average of these 2 units. All right, so that's what B is. C, the bottom left corner, says, well, now let's do the same thing, only now we're going to take 10 units. All right, so out of these thousands of units, we're taking 10 units on average and looking at it, and we're getting closer to the fact that the majority of time these units require about an hour of work on them. Sometimes when we randomly pick 10 units, they don't need much work at all. Sometimes they need a lot of work. And it keeps going like this even when we get down to 25 units. We now have a much more normal looking distribution where we have an average, 25 units. So again, if I randomly pick 25 out of this entire population, most of the time they need about an hour of work. Sometimes they need more, sometimes they need less, but the majority of times the average of those 25 picked at random is going to be here. And so you just kind of trying to illustrate that when you have something that is skewed and you start taking basically random samples, the more random samples you have, the closer you're going to get to the point where you have a normal distribution where the mean is also the average. All right, so the mean of the population over here becomes the average of the sample here. And notice that it becomes more normal, so it's something that we can use in order to statistically talk about, how many units are going to take more than an hour or less than an hour. So that's the introduction to this. What we actually have in this one is we've got this idea that with all of these units, here is the normal. So this is for the entire population. We have a distribution. I shouldn't even say it's a normal distribution. We have the population has an average of 1 hour with that standard deviation of 1 hour. All right, we are being contracted to service 70 of these units in an apartment building. All right, so they basically say, let's assume that this 70 units is going to be our single random sample. All right, and they want to know Is 1.1 hour or 1.25 hours a better scheduling time slot? All right, when we send guys out here, we want to know, should we be having them schedule 1.1 or 1.25 hours? Remember, when we were looking at this, the average is going to be 1 hour. So 50% of the time, it's going to take them 1 hour or less. All right, but that means we'd have 50% of the times they were staying too long if we only schedule an hour. So we need to schedule a little bit more than an hour. So they want to know, should we be 1.1 or 1.25? And basically we want to know, well, how often are we going to be over the time estimated? So we're trying to figure out what percent is over here. All right, so what we need to do is we need to take the original information and we need to understand what's going to happen with our normal distribution. So the one that I just pointed out. So I'm going to redraw our normal distribution and make it a little bit bigger. All right, so here's our 1 hour. And I need to know, like, where are these standard deviations at? All right, so what is this? And in order to do that, we are using the central limit theorem, which says we're going to have a normal distribution where the average is still the average, but our standard deviation is going to be based on the population divided by the square root of the size of our sample. All right, so what this means in ours is that we had 1 hour and 1 hour, but we're going to take this standard deviation and divide it by the square root of 70. So that is why they have 1 and 1 hour divided by the square root of 70. All right, so if you follow along, then they say that this is 1 with a standard deviation of 0.12 hours. All right, so here's 1.12, here's 1.24, here's 1.36. Now, if you remember as we went through here, these are right on the standard deviation. I'm going to show you how to use the z-score table, but I should know that from here all the way up to the average, that was 50%. If you remember our 68 rule, this is 34% going up to the next standard deviation. So according to this, if I scheduled 1.1, I know already that I am going to be late at least 16, a little bit more than 16% of the time. All right. If I schedule 1.25, if you go all the way over to here, I know I'm going to be on time a lot more often. So I'm going to guess that it's the 1.25, but let's see how late we are. So I've got this idea of the standard distribution. Now we have to use that z-score. So I want to check what is the z-score for 1.1 hours. So remember, I take 1.1 minus the average, divide it by my standard deviation of 0.12. I'm going to do the same thing for the 1.25. All right, and I'm going to crunch these two numbers here. So 1.1 minus 1. Not going to use that calculator is busted. So 1.1 minus 1 divided by 0.12. Let's see. I got a calculator around here somewhere. Where is it? There we go. .83. And this one, 1.25 minus 1 divided by 0.12. Equals 2.0. Now these are not the percentages. These were the z-scores. Now I have to use that table, the z-score table. So I'm going to look them up. And again, this one, you can use a number of different things. I'm going to use the ones in the back of the book. So for 0.83, I get 0.7967. So that's about approximately 80%. If I do 2.0, I have approximately 97%. Remember, that's telling me that I am going to be late. All right, 80% goes from here all the way up to 1.1. So I'm going to be late 20% of the time. Here, I'm only going to be late 3% of the time. So I think it makes more sense for us to schedule a 1.25 hours than it does to schedule 1.1 hours. All right. If it was, the difference of maybe 1 or 2%, I would probably say you could schedule either of them. Now, we could be really safe. If you remember how this works, 1.36, that's going to be 99.85% all the way up to here. So if you scheduled 1 and 0.36 hours, so 1 hour and 20 minutes, you'd be on time just about every time. So that's a difference of 5 minutes, and it might not seem like a lot, but I suppose if you're running a company and doing this a lot, that extra 5 minutes of labor is going to be a big cost savings for how much you have to charge the customer, as well as how many of those things that you can get done in one day. So that is why they are working towards this 97% doing 1.25 hours. Figuring out what percentage would take less than 1.25 hours. Using the normal curve with the normal distribution and the new information of a standard deviation. So remember, when you're looking at this, the standard deviation here, this isn't even a normal curve, doesn't help us very much. So as we take more and more samples, you get more and more normal. And then you can use that sample size based on how many of these how many things are in that sample, it gets more and more normal. So we're doing a sample of 70, it's going to even be more normal looking than this one is. All right, and that's where they get that standard deviation for us to calculate in here, and that is their exercise 11.8 or example 11.8 and how they worked through that. So that's exactly what you're going to be doing in 11.13 for Friday.